Hello and welcome everyone again. This time we'll take a look in details into the gradient, divergence, and curl. Probably you are already familiar with these three terms, but not in detail. So we'll take a detailed look into those things regarding what they mean, or the general formula to calculate those things, etc., etc. Let's have a quick look back at the differential quantities that we have already calculated or derived. For Cartesian system, the differential length vector was somewhat like this. It says for any differential displacement in a 3D space, you can break it down into its three components along the three axes, namely the ax, ay, and az, and the individual differential quantities would be just dx, dy, and dz. But in case of the cylindrical system, there is an angle associated with it, right? So in case of the radial differential quantity, we have no problem because it's already a length. So we can convert r into dr, and this also applies when we're dealing with the dz quantity. But in case of the phi quantity, we have to convert it into the distance covered, so we have to multiply it with radius. So we have discussed this already, I think. And in case of the spherical system, the case is almost similar, but in this case we're dealing with two angles instead of one. So there are two conversion factors that are being multiplied with each of the d theta and d phi quantity. Alright, so in case of the spherical system, we are using r as the conversion factor for d theta, and r sine theta as the conversion factor for d phi, to convert the respective differential angle changes into the respective length changes. All right. So if we write down the general formula from this, we can write it as dl for any coordinate system as a unit vector, a conversion factor, times d variable, right? So this would be the general formula of differential quantity in any coordinate system, and depending on the coordinate system you're using, the conversion factors will change. So in case of in case of the Cartesian coordinate system, we're just using dx, dy, and dz directly. So there is no conversion factor. Alternatively, the conversion factor we're multiplying with dx, dy, and dz is 1. I mean, whenever you're writing this thing, it's the same as writing it as 1 into dx, 1 into dy, and 1 into dz, right? So in case of the Cartesian coordinate system or any differential quantity that incorporates length, will have a conversion factor equal to 1, right? So the convention that we would be following will have h as the conversion factor and u as the axis variable. Alright, so let's say, for example, in a 3D space, we don't know the system already. It might be Cartesian, or might be cylindrical, or might be spherical. We don't know yet, but we know that in 3D space we have to specify the position of a point with three variables, right? So in case, so we can denote the unit vectors associated with the axis variable with AU1, AU2, and AU3. Alright, so the A bar means the unit vector, and the subscript named u1, u2, u3 denotes the axis variables, alright? So if we're talking about the Cartesian coordinate system, the u1, u2, u3 converts into x, y, and z. In case of the cylindrical coordinate system, u1, u2, and u3 converts into r, phi, and z. And in case of the spherical system, the value of u1, u2, u3 converts into r, theta, and phi. Alright, so let's just keep that in mind. This is the general notation that we'll be using. And for the conversion factor, of course, we'll be using h1, h2, and h3. So if we just look at the three differential length vectors in case of the three coordinate systems that we discussed, they all follow a general format, right? This general format looks like this. AU1, the conversion factor associated with the first variable, H1 du1, AU2 H2 du2, and AU3 H3 du3. Alright, so whenever we're going with the Cartesian coordinate system, H1 equals to 1, H2 equals to 1, and H3 equals to 1. Remember again, H1, H2, H3 are the three conversion factors used for dx, and dy, and dz. Alright? And in case of the Cartesian coordinate system, obviously as shown here, u1, u2, and u3 are x, y, z. So au1 is ax, au2 is ay, and au3 is az, or az, whatever you say. In case of the cylindrical coordinate system, however, h1, the first conversion factor for dr is 1, obviously, dr already being length. H2, however, will be r, and H3 will be 1. I guess this is clear from the expression above. If you look at here, the d phi quantity has an r multiplied with it to convert it into the length traversed. So the conversion factor here is r, and the conversion factor is h2 over here. All right. And in case of the spherical coordinate system, we have h1 equals to 1, h2 equals to, I guess it's clear now, h2 should be r, and h3, the third conversion factor, is r sine theta. Alright? So this is the general notation that we'll be using in case of the differential quantities, and just stuff in all the relevant variable names or conversion factors as we select the specific coordinate system that we will be moving forward with. And this expression is important because when later on we will be taking a look at the gradient averages of the curls, the general formula, these notations will come in handy, because we'll see in a while that the format of the formula of gradient, the formula of divergence, and the formula of curl varies from system to system. Alright, so we'll have to denote the general formula with the general notations like this.